As requested, Team 38 has produced a solution for the Global Emergency Autonomous Response System, or GEARS, in accordance with the request for proposal issued by L3Harris. We are proud to present a brief summary of what we think is a strong option for this complicated problem. To start out, here are some of the main objectives that we identified in the development of our GEARS solution. We wanted to make sure to design a prototype for an autonomous system that will transport supplies to civilians in disaster zones. Furthermore, we wanted to develop an algorithm that will precisely navigate the GEARS through the designated disaster zone while successfully avoiding hazards such as magnets or high heat. We also had to model a container that will safely contain the supplies during their journey in the disaster zone, while also being comprehensible across a broad variety of cultures and languages through a cargo label system. Finally, we had to return a live map of the disaster area to the base station in order to further explain how the GEARS is navigating and where the location of the hazards are. In order to better manage the project, we used several strategies, including creating diagrams to help visualize tasks and dedicating members of the team to sections of the project in which they could be most efficient. As you can see, the WBS we created clearly breaks down the project into simple tasks that could then be handled one at a time. These include things such as creating the cargo holding system or making a high temperature heat detection system. To the right, you can also see the work breakdown by member. Before launching ourselves into the building of the prototype and development of the software, we created several tools to encapsulate the main functions and target goals needed to successfully achieve this project. On the left, you can see a table of technical specifications that turns the demands from the RFP into requirements and target values. These include making metrics to success for things such as detecting hazards, avoiding hazards, or producing useful maps. This aided in determining how successful our GEARS system was in terms of the software and also the prototype and models. The functional block diagram also aided the team, especially in the brainstorming process, as it provided a general overview of the project without making any limitations to possible solutions. The GEARS prototype envisioned by Team 38 has many unique features. It is built on a compact and innovative 6-wheel chassis design that has 2 large power wheels at the center and 4 smaller wheels located on the outside for stability purposes. This allows the GEARS to perform point turns without changing the position of its center. This proves to be useful in navigating in tight spaces and in junctions. It also has 3 ultrasonic sensors, one on both sides, left and right, and one in the front. These communicate with the Raspberry Pi to ensure flawless navigation. The GEARS also features a top-mounted cargo bay with an innovative support system that consists of a pin locking mechanism to secure the cargo, while also allowing it to be easily removed. Finally, its low center of gravity gives it great maneuverability, especially in rough terrain or narrow areas that may be present in the hazardous zone.
In order to design the cargo, we first determined our priorities. After brainstorming, we decided we wanted the design to be as simple as possible to aid ease of use, as compact as possible, and as durable as possible. After determining these, we began to determine what shape the cargo would be. After the preliminary design process of the GEARS, it was determined the best place for the cargo would be on top of the system. Because of this location, the cargo had to have either a rectangular or square base. In order to optimize the volume, the cargo was going to either be a cube or a rectangular prism. Finally, in order to minimize the effect on the movement of the GEARS, the cargo was designed to be smaller and easier to transport. The final design is shown in the images on the slide. The hinge is a simple ball and socket joint to aid ease of human-powered opening and manufacturing. The lid is held in place by a small snap closure, as you can see on the bottom image. The labels are interchangeable on their platforms, but only one is shown for example. The final dimensions of the cargo are 3.9 centimeters by 3.7 centimeters by 2.4 centimeters, which leads to a final cargo capacity of 207.8 grams. The cargo will attach to the GEARS system with ratchet straps to facilitate ease of use. Finally, the cargo will be made out of high-density polyethylene for its ease of use, durability, and the ability to be recycled. Once the cargo was designed, labels to depict what the container held were needed. To begin the design process, we researched different symbols across cultures. In this research, we found a study published in the Journal of Augmentative and Alternative Communication that found that the most recognizable set of symbols across a number of cultures was a system called PCS, which stands for Picture Communication Symbols. An example of these symbols can be seen in the picture on the right corner. After seeing a number of these examples and determining what made a symbol memorable and easy to recognize, simplicity and color, we began to design options for each category. Once 2 examples were created for each symbol category: shelter, food, fuel, water, and medical supplies, a survey was created that allowed participants to choose the symbol they believed best represented each category. The results of this survey will be shown in more detail on the next slide, but the symbols with the purple outline were the chosen symbols. The final piece of the cargo system and communication was the sound to be played once it was safe for the recipients of the cargo to retrieve it. After researching numerous different ideas, including different languages, music, and types of sound, it was determined the best choice was pink noise. This is a type of noise very common in biological systems and is a very non-threatening noise. This was chosen over other forms of communication because there is no language or cultural barrier with this type of noise. It would be played based on motion sensing to indicate safety when people were around the cargo. An example of pink noise can be heard here. As mentioned in the previous slide, these are the results of the cargo label survey. This survey took the ages, countries of origin, and if from the United States, region the United States of origin. The survey had a total of 44 participants from 4 countries and 3 out of the 4 regions of the United States, with ages ranging from less than 10 to over 70 years old. The other 5 pie charts depict the breakdown for the winning symbols in each category.
So, our navigation algorithm takes inspiration from Schumach's research and works as follows. Step 1. Follow the initial hallway until an intersection is reached. Step 2. Turn right if able to, otherwise go straight. If this is not possible either, turn left, and then go back to step 1. A pro of this algorithm is that it is guaranteed to work in any maze setting, as long as the walls are defined. However, a negative is that it does not always navigate using the shortest possible path, which we are okay with because we decided that using a more complicated algorithm might not be worth it. This algorithm also implements PID control. This guarantees that the adjustments made are efficient and allows the system to navigate through tight spaces. Lastly, it takes the average of the right and left ultrasonic sensors in order to follow the middle of a path rather than a specific side. This is implemented so that the gears doesn't accidentally hit the wall while navigating the maze. It also allows it to go in a straight path more easily instead of veering from left to right. So the mapping algorithm is implemented with the navigation algorithm. It works by marking every block that is successfully crossed while using the navigation algorithm with a 1. When all 3 directions are blocked, so when the gears reaches a dead end, it places a 0 on every block that is traversed until a marked block is again reached. A 5 will be used to represent the start of the maze, and a 4 will be used to represent the exit of the maze. The numbers 2 and 3 will represent heat and magnetic sources respectively, as they are detected in the maze. The result will be similar to what is displayed on the right, but formatted as a comma-delimited Excel file. The empty spaces will be represented by zeros, but were left out for demonstration purposes. When we are navigating the maze, these paths will not be discovered by the gears, but this is okay since it ends up being more efficient. However, when we just need the maze to be mapped, we can quickly adjust the code so that the robot doesn't stop after reaching an exit and therefore goes through the whole maze.
In order to identify the possible cultural and ethical implications of using the Gears unit in a disaster zone, we performed research on people's reactions to disasters and their attitude towards robots. As shown by a survey done among earthquake survivors in Agadir, Morocco, some cultures place more faith in their beliefs than the physical things protecting them from a disaster. Some even believe that the effects of a natural disaster are a punishment for their sins. Other effects that can influence people's reactions to disaster include psychological effects, as well as pre-existing social and economic conditions. This is especially common when those pre-existing conditions influence how people prepare for and are educated about possible disasters. People's attitude towards robots also differs greatly in various regions of the world. A study done in 2005 analyzed the differences in attitudes towards robots in the Netherlands, Germany, China, Japan, Mexico, and in the US. The results showed that the US has the most positive attitude towards robots, and Mexico has the least positive reaction to them. In order to use the Gears unit to its full potential and make it truly scalable, research would have to be done on the attitudes of people in a specific area on a case-to-case basis. If the reaction to robots is too negative, we may have to consider alternate methods of emergency supply delivery. There are some areas in which we could still improve upon the Gears unit. The latching system on the cargo lid has not been fully tested due to the fact that we didn't have the necessary resources to 3D print it. Also, the sensors and motors are imprecise and don't return decimal values, which limits the accuracy of readings and could possibly limit the unit's navigational capabilities. There are some improvements we would like to make if given more time and resources. We believe that it is possible to create a more efficient algorithm to solve the maze by finding the shortest path. We would also like to modify and test the latch system to be more stable. Possible physical improvements to the Gears unit could be using more precise and powerful motors to increase the speed and braking in order to reach the destination faster, and using a gyroscope sensor instead of time to measure turns more accurately. In conclusion, we believe that our prototype Gears unit is easily modifiable and adaptable to fit a multitude of scenarios, including natural and man-made disasters. Based on survey results, we are confident that the cargo symbols can be easily attributed to their relevant categories across a variety of cultures and languages. Unfortunately, we were unable to test our final prototype, but based on the limited physical testing that was performed and the development of our algorithms and models, we are confident that our Gears unit would be able to complete the assigned task with a moderate to high level of success.